This presentation shows a potential solution which all of or part of it may be used to potentially stop the BP oil leak in the damaged well in the Gulf of Mexico. This solution consists of an Insertable Pressure Assist Cutoff system, for short IPAC system, which uses a plunger type valve that basically rotates on a plunger system that is inserted into the oil pipe and then locked in place to shut off the flow of oil. The simulation shows how the device is inserted into the oil pipe, and upon insertion, these blue areas here are alignment flanges. There's 3 of them, which you can look down here at this lower figure, which is a rear view based on this angle right here, looking straight down the pipe, of how these basically these flanges will protract. They're heavy spring-loaded flanges that are mechanically protracted once they enter the pipe to stabilize the system. If you look in this lower figure here, once the system enters the pipe, you can see how these flanges are retracted to stabilize this system and then begin inserting it the rest of the way into the pipe. Once the IPAC system has been fully inserted into the pipe, the robots are going to insert through pre-drilled holes the retaining pins that are required to hold the IPAC system in place. And you can see the retaining pins going into the pipe now. And basically once they're inserted, there's a retention flange that's on the main superstructure of the outer portion of the IPAC assembly. And once the assembly is released by the device forcing it into the oil pipe, that flange will butt against the retention pins and the IPAC system will be held in place. At this point, the retention flange, flashing blue here, has not been shown on the head-on view simulation. We're going to show that flange now, and you can see how the retention pins come in to the pipe from the head-on view and butt against the main structure of the IPAC assembly to hold it in place. It's important to note during this process that oil is allowed to blow by the IPAC system during assembly to reduce the amount of force required to insert it. The lower animation here, you can see the red flashing area, the red alternating red and yellow, is the area where the oil can actually pass by the IPAC assembly during the insertion process, so you're not trying to cut off, or you're not inadvertently cutting off the flow of oil, which would dramatically increase the pressure and the amount of force required to insert the IPAC assembly. After the insertion process, a mechanical locking mechanism is disengaged, shown here in the rear, and when that happens, the center assembly of the IPAC system is going to be able to slide, allowing the valve to be pushed back by the oil pressure ramming into it. This strut's going to provide torque to the valve, rotating the valve and closing it shut, as this animation will now show. Thus you can see how the valve will be closed as it moves back and cutting off the oil flow. You can see that again in the lower animation, looking at it from the head-on view, how that happens. The next backup system we're going to have on this is basically what amounts to a large threaded nut that can be turned by the robots to extract the center portion of the plunger assembly of the IPAC system, to be able to extract it manually. And we're going to show that with this animation here, how when that nut's turned, it'll pull the center portion of the IPAC assembly out, forcing the valve closed if for some reason the oil pressure does not close it. I'm just going to briefly summarize some of the system advantages and primary physical requirements to implement this potential solution. One of the main system advantages for the IPAC system is it does not require the robots to do any complicated tasks below the surface. They basically help stabilize the IPAC system upon insertion against the oil flow when it hits it, and also they're required to drill 1 or more holes in the oil pipe for the retention pins to be inserted to lock the IPAC system into place before engaging it. Secondly, the IPAC system allows a significant amount of oil blow-by during the insertion process to minimize the amount of force required to insert the system. We're not blocking a majority of the oil flow upon insertion, which would greatly increase the amount of insertion force required to actually place the system inside the pipe with the outgoing flow of oil. Thirdly, it's going to utilize existing oil pressure to close the valve when the oil pressure rushes against the oil flow rushes against the valve. Fourth, this particular IPAC system is very simple in design. There's no hydraulics involved. With the exception of the O-ring on the valve, you may want to implement some hydraulics to expand that to help decrease the oil flow. But other than that, this system, there's no reason it can't be designed and actually built in 7 to 10 days. Primary physical requirements, number one is going to be the pipe entrance can't be too badly deformed. You need a uniform pipe entrance to insert the assembly or the IPAC system into it so it won't be blocked upon insertion. Secondly, you're going to need about 6 to 8 feet of uniform pipe hollow to insert the IPAC system in before engaging it. And thirdly, we're going to have metal alloys that are strong enough that once the system's engaged and it shuts, that the metal parts restricting the system from being ejected, particularly the retention pins, are going to have to be strong enough to withstand the shear forces and the compressive force. The second video, part 2, is going to show a video simulation for one method of installing and engaging the IPAC system.